okay, is I can call that revision because I remember I teach this in year 11. I'm not sure if you remember or not. If you don't remember, this is a new lesson for you. If you do remember, that's a revision for you. We'll go through one really important question in the end, but like that's after I go through all of the content here. So discrete random variable. We are introducing this idea here. What is discrete random variable? So you know, from year 9 to year 11, what all you learn is to describe an outcome. So we toss the coin 3 times. We get heads, tail, or head, tail, head, or like something similar to that. We describe the outcome. Now we want to change all the outcomes to numbers. Something can easily, like I can make you easily understand is for the head and tail questions. Okay, if you can go to the next page. For example, I'll just show this example while I'm doing this concept. Tossing a coin 3 times. Okay, you know there are 8 outcomes. Okay, if you know that. Let's just draw the tree diagram. I draw it backwards. Because I want the tree diagram looks better. Okay, so that's the first one, second one, and third toss. Okay, so that's what the tree diagram looks like. You can draw from the first one and then to the third one. That's how the tree diagram looks like, and every branch with a probability of a half. Okay, every branch with a probability of a half. Every single outcome. So this outcome is head, head, head. That's head, head, tail. Head, tail, head. Head, tail, tail. Tail, head, head, tail, head, tail, 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 head, and tail, tail, tail. Okay, they're all descriptions. Okay, describe the order and what we get as well. All right, now let's read the next sentence. You don't really need to finish this tree diagram, just like an example to show you. It's more important to understand what is it. So the next sentence is define something. I have defined the capital X as the number of heads obtained from this experiment. Okay, so I tossed the coin 3 times. How many heads I can have? What's all the values I can have? What X can be? 0? 1, 2, 3. Okay, I have no head, 1 head, 2 head, 3 head. So look at each of these outcomes. This is the outcome. But this is the random variable X. Okay, so X represent what? Represent the number of heads I have in each outcome. So I have 3 heads in this outcome, 2 heads in this one, 2 heads in this one, 1 head in that one, 2 heads here, 1 head here, 1 head here, and 0 head in this case. So you can see that's all the values of X I can take. Why is it called random variable? Okay, first of all, it's random outcome. Okay, I do this 3 times, that random outcome, that random experiment. Second variable is changing, it's varying. Okay, the X is not always take 3, always take 2. It's changing from 0 to 1 to 2 to 3. Like, depends on different outcomes you get. The third thing I want to talk about is when X equals to 2. You can see there are 3 things gives you X equals to 2. So when I said X equals to 2, all you know is from the 3 tosses, I have 2 head and 1 tail. That's the only thing you know. That's the final result. But what you don't know is, do you have the tail first, or do you have the tail in the middle, or do you have the tail in the end? That's what you don't know. So the order is not taken into consideration. Okay, the order is not taken into consideration. What all I have is the final outcome. Okay, in the end, what I get 2 head and 1 tail overall. But what I don't know is the order. So when we talk about random variables, order is not taken into consideration. So it's not really, I don't care about what do I get first, what do I get second. It's overall, in the end, what do I get? Okay, so now I want to convert that into a probability table. Okay, or it's called a density table, or you can call it a distribution table. So what this table consists of, I make X become my random variable, so I will have 2 rows. The first row is a lowercase x. The second row is I can write in two ways. First is PR, capital P, lowercase r, capital X equals to lowercase x. That's the first way to represent the probability. Okay, this is some notations. You may be confused about that. Just remember what the notation should look like. The up one is a lowercase x, and the bottom one is a capital X equals to lowercase x of PR. So, or another way to write it is lowercase p, lowercase x. Okay, or px. That's another way to represent the probability of taking that x. So what is your x value? I will write x from the smallest to largest. So the four values this x can take is 0, 1, 2, 3. It needs to include everything. Okay, all the x values you can take. That's 0, 1, 2, and 3. So what's the probability? Okay, the next line represent, this line represent the probability of your random variable x takes this particular value. What's this particular value? This one's taking the 0. So it's one probability, random variable equals to 0. What's the probability of getting that? That's 1 on 8. Because there's only one such outcome, give you 0 hat, and that's 1 on 8. Similarly, you have 1 on 8 for the random variable takes 3. Because you want to obtain 3 hat, it's only the first situation you will get. So that's 1 on 8 as well. What's the probability of taking 1 hat? Okay, or taking 1 hat. To take 1 hat, I have this case, and this case. There are 3 situations I can have 1 hat. So that's a 3 over 8. Okay, why 3 over 8? Because each of the situation got 1 on 8 of the probability. So I have 3 such outcomes. I have 3 over 8 to get probably x equals to 1. And then 2 has 3 over 8 as well. 1, 2, and 3. Okay, this x is a random variable. It changes your outcome, describing the outcome into numbers. When you see the number, you kind of know what you get already. As I said, there's limitations. You won't know the order, but you know in the end what I get overall. I get 2 head, for example, the 2, I get 2 head and 1 tail. Or the 0 means I get 3 tails, no head. So you know overall what you get as outcome. So it will combine some of the outcomes together. I just care about the number. Okay, this one's easy. You might think, oh, you toss the 3 coins and you talk about the number of heads. That's easy. How about if I have a trial is observing the weather tomorrow? Okay, observing the weather tomorrow. I can also make a random variable x. I want to see whether tomorrow is sunny or not. Okay, it's sunny or not sunny. So I can say the random variable x is sunny tomorrow. Okay, x represents sunny tomorrow. X equals to 1 represent is sunny. X equals to 0 can represent is not sunny. So I can define things by myself. Okay, I can give outcomes like as numbers, and I can use the number to represent particular outcomes. So that's something called random variable. So change word into numbers. Okay, change word into numbers. All right. Let's go backwards to the previous page. Some notations they also talk about. Capital letters. Capital letters represent random variable. Is the thing can change. Okay, every time you say PR something equals to something, this is the capital letters and this is the lowercase. Okay, it's the capital letters and the lowercase equals to lowercase x. So it must be capital equals to lowercase or capital equals to a number. That will be the notation, okay? Or a number, so that will be the notation. You must use capital X to represent random variable. Every time we define things, you need to define that as capital letters. That's just a notation thing. And as I said, there are 2 types of random variable. The first type is called discrete, and the second type is the continuous. Chapter 13 and 14 is on discrete, and chapter 15 and 16 is on continuous. Okay, chapter 15 and 16 is non-continuous. So what is discrete random variable? A misconception here is discrete random variable is not always integer values. Discrete means countable outcomes. You can count how many numbers you can take. But the number can be anything. It can be decimals, can be integer, can be third, can be irrational numbers. Your what x can take can be anything, but it just needs to be countable. There are countable outcomes you can have. For example, the shoe size for female. You might have start from 35, 35.5, 36, 36.5, 37, 37.5, until maybe 45. We take 0.5 values, but how many outcomes do we have? We can count 35, 35.5, 36, 36.5 until like 45. I can count there are say 15 size or 16 size, but I can take decimals. What is continuous random variable? Normally we have measurement values, usually generated by measuring. Okay, so you measure something, these values are normally continuous. Okay, the example I always use is like water bottles. What's the water in the bottle? From 0 millimeters to 600 millimeters. Every value in between 0 to 600 is, I can get, because even though you can't measure it, okay, you measure it that, you will correct to 1 decimal places, for example. That's because you can't measure. It doesn't mean it doesn't exist 0.00001 liters. Like, it's still possible to have volume of that much in this bottle. You just can't measure it. Like, it doesn't mean it doesn't exist. So measurement is normally like continuous. For example, the height, the weight. Again, like, you can't measure doesn't mean it doesn't exist. So I can have any height in between 1 meters to 2 meters, for example. So any height in between is achievable. So that is continuous random variable. Time, the time to complete running for 100 meters, that can be continuous as well. It's the time taken from 10 seconds to 20 seconds, for example. Any time in between is possible. Okay. Now we are going to introduce what is a discrete probability distribution. Okay, what is a discrete probability distribution? Okay, this is a discrete probability distribution. That's one of the form. Okay, what I give you the table, that's one of the discrete probability distribution. What is distribution? Okay, what is distribution? Distribution is telling you what you have and how the probability is assigned to each of the values. So from this table, can you see clearly? You can see clearly x is 0 to 3, 0, 1 to 3. And you can see clearly each value with a probability of 1/8, 3/8, 3/8, and 1/8. So it's just telling you how this, the allocation of all the probabilities to each numbers and what numbers you can take. This is called a distribution. Sometimes, well, for a table, it's very clear to see what the distribution is. Like, what's each probability for each individual values. You can have other forms. What's the advantage of a table? Clear. Okay, easy to read. I can see it directly. What's the disadvantage? How about if I have x can be 0 to 100? 101 values. Are you going to list all of it? Too big. Like, the table can be too big and it's not really that useful. So we have short like tables, like we have some values, like 4 or 5 values. It's very good to use a table because it's clear. So how about if the thing is not small, like you have more values for x? You can use that a mass function. Okay, you can use a mass function to represent, instead of listing out all of it, you can use a mass function. So what is a mass function? Example 4 is mass function. Okay, example 4 is mass function. You have px equals to that, but the probability is changing with the x change. So also you can list out what your x can be. Your x is 0, 1 to 3. Okay, x is 0, 1 to 3. And you can sub x into the function to get the probability for x equals to 1, x equals to 2, and x equals to 3. So this is a mass function. Also, I want to add another one. I can use Well, it's not really that useful, but it's still possible to have. I can use a graph, like the dot graph, to represent the distribution. So what's the example for that is, if you go to page 8 of example 1, that's a graph represent the probability. So how to read that? When x equals to 1, you have probability 0.2. When x equals to 2, probability equals to 0.3. When x equals to 3, probability equals to 0.4. And when x equals to 4, probability is 0.1. Yeah? It doesn't matter, because every discrete probability distribution, I will convert into a table first. Okay, everything you have in year 12, you will convert that into a table. Everything discrete. Okay, just doesn't matter, give you a graph or give you a function, you convert into a table what x value can be and what's the probability of it. Why I'm doing that? Next lesson I will go through this. Okay, so that's this. Okay, now we said let's just randomly draw a table. Okay, let's really randomly draw a table, really randomly give some values. Do you think any table can become a discrete probability distribution? Is that possible? I just draw any table and represent probability distribution. No, it's not going to be true. So what's there? Two requirements, like two conditions it must satisfy to become a probability distribution table. So the first one is each individual probability in the second row, it needs to be in between 0 to 1. So which means all of these values needs to be in between 0 to 1. Okay, all of these values needs to be in between 0 to 1. Next, the next thing is when you add all the probabilities together, you will have 1. So you're adding this row together, it needs to be 1. That's the two requirements I have. Do we have restrictions for the first row? No. Okay, no restrictions for the first row. First row can take whatever you want. Okay, there's no restrictions for the first row. For the second row, you need to have each individual probability in between 0 to 1, and adding all of the probabilities, you should have 1. Okay, by knowing that, can you have a look at A? Ignore what I write here, that's for the other class today. Have a look at the 4 tables below A, B, C, D. Can you tell me which one can represent a discrete probability distribution, which one cannot, and why? Okay, so you have A, B, C, D, 4 tables. Which one can become probability distribution? Which one cannot become probability distribution? How about the first one? Yes? Yeah, first one, good. So, yes. How about B? Yes or no? Yes. If you see, well, 0.5, 0.3, 0.1, 0.1, good. Adding them, 1. Okay, B is good. How about C? Where's wrong for C? Okay, it doesn't add up to 1. If you add all of that, 6, 7, 8, 9. That's a 0.9. Okay, this one can't work. How about D? Which wrong? The negative is the obvious one, or if you add them, it's 1. If you add them, it's 1. But because there's a negative probability, that's wrong. Okay, so negative 0.2 can't work. So D is not. It's very easy to decide whether they are distribution table or not. Okay, if you have your calculator, or if you can share calculators between 2 or 3 of you, ignore A and B first. You can do A and B by yourself. I want to do C. Okay, I want to do C in class. Find the values of K for which the following discrete, it is discrete probability distribution. Okay, all the 3 tables here, they are discrete probability distribution. So can you find out the K values for C, please? If you have calculators, you can use calculator. If you don't, you can do it by hand. Okay, first of all, that should be the equation you put into the calculator. Anyone find k values already? Yes? Yep, k equals to 0.1 or k equals to 0.4. Okay, if you use calculator, you should have this value if you enter everything correct. My next question is, can I take both values? Okay, someone say no, which one can't? Why 0.4 can't? Yep, if you sub 0.4 into this one, the individual probability is not in between 0 to 1. It will become negative 0.1. See, if I sub 0.4 back into the equation, you have negative values. So 4 can't. Sub and check. Okay, you always need to satisfy two requirements. First one is each individual probability is in between 0 to 1. Second is all the probability adding up should give you 1. So if any of this does not satisfy, you can't have a probability distribution. So when we set up the equation equals to 1, that's only the first thing we do. Okay, that's only the first thing we do. We satisfy condition number 2. Then we need to check about our condition number 1. So sub and check. So k equals to 0.1 only for this question. Okay, equals to 0.1 only for this question. Okay, let's have a look at example 4. Example 4, show that the function px equals to 1 over 42 5x plus 3, where x can be 0, 1, 2, or 3 is a probability function. Okay, it's the same as how do we test for a probability distribution table. What we can do here is, as I said, you can always convert things back into table. I have x and I have lowercase px. I have 0, I have 1, I have 2. Okay, I have that. Okay, px, when x equals to 0, okay, I can have 3 over 42. I know I can simplify it, but just leave it as this for a second. 1 sub 1 in, I have 8 over 42. Sub 2 in, 13 over 42. And 3 in is 18 over 42. Okay, so after you set up the table, what you can say is, first, px is in between 0 to 1 when, or say for x belongs to 0, 1, 2, and 3. That's the first condition. All the probabilities needs to be in between 0 to 1. Or there's another way to write this. Ask a question. What's the probability when x equals to 4? When x equals to 4, what's the probability? It's not the domain. It's not the domain. What's P4 should be? Is that possible to have 4? According to your question, like x belongs to 0, 1, 2, 3. It's not possible to be 4, which means the probability of getting 4 is what? 0. Okay, the probability of getting 4 is 0. So another way I can write this, or a better way we can write this, is probability of x is in between 0 to 1 for all x. Why I say for all x? for any x not listing here, for any x which is not 0, 1, 2, and 3, I can say its probability is just 0. To get 0 is fine. To equals to 1 is fine. To get beyond 1 or less than 0 is not fine. So if my px is in between 0 to 1 inclusive, that's still satisfied. So I don't need to really emphasize what x do we have. I can just say for any x values, my probability is in between 0 to 1. Because when we have x not belongs to the domain, the probability is just 0. Okay, it's just 0. And the second, what I can do is the sum of all the px for x, that equals to 3 over that plus 8 over that plus 13 over that plus 18 over that. So it's 3 plus 8 plus 13 plus 18 over 42, and that is 42 over 42, and that equals to 1. Because it asks you to show, so better show more steps to show why that equals to 1. Like, I know it's quite, why we should do that. We can see that's 1, but like trying to show a couple of more steps, that's what we can do. So it's 42 over 42, yeah. Sum of all the possible x. The x means the values you can take. You don't need to really know this notation. It's not really in the study design, but you can just start from the next, the 3 over 42 plus 8 over 42. Start from that. Any questions? Okay. If don't have any questions, I'll skip the next 2 questions because they are exactly the same thing. Don't need to do that now. I want you to have a look at example 6. Okay, I want you to have a look at example 6. Example 6 said a card is chosen randomly from a standard deck of 52 playing cards. A second card is then chosen randomly. Okay, I have picked 2 cards from 52 cards. Let X be the number of clubs chosen. How many clubs are there in 52 cards? How many? Sorry? 13. Okay, 13 clubs. Okay, how many cards are not clubs? Yep, 39, not clubs. Okay, so construct a table of probability distribution for X. So I want you to set up the table like this. Okay, give me a table. Represent the number of X. Okay, first of all, what X can be in this question? What X can be? X represents the number of clubs chosen. How many cards you have chosen? How many cards in your hand? 2. How many clubs do you have then? 0, 1, 2. Okay. Now what you're trying to do is find the probability for 0 club. How I can have 0 club? Probably how can I get 1 club? Probably how can I get 2 clubs? 2 questions. First question asks you if each card is being replaced. Like when you replace the card before the next card is chosen. The second one is after you pick the card, you're not putting it back, and then pick the second one. So with replacement or without replacement question. Okay, so do 2 separate tables for me. First one is easy. You can set up tree diagram for both of that. I give you let's say 10 minutes, about 10 minutes to figure that out. And I'll go through this with you. There's a really important concept is in this question for the second part, for B. Okay, so try what you can do first, and I'll show you what I can do. Okay, with replacement and without replacement. The first one is called a binomial. The second one is called a hypergeometry. I think last year you should be taught that already? Okay, if not, you may not know the name, but like you might know what we're doing. Okay, let's have a think. We just think about tree diagram first. Okay, that's what everyone's doing. So for A, I can choose club, not club, club, not club for the second time. For the first time, I have club, not club. Okay, I still draw it backwards. The probability of getting a club is 1 on 4. The probability of not getting a club is 3 on 4 for your first time. For the second time, because it's replaced back, it doesn't matter what you have been selected for the first time. They are independent events. Okay, they are independent events. The second time and the first time, they are independent. So it's a quarter, 3 quarters, a quarter, and 3 quarters. The probability of getting that is 1 on 16. That's 3 on 16. That's 3 on 16, and that is 9 on 16. And according to the x values, is the number of clubs we get. So number of clubs I have here is 2, 1, 1, and 0. Okay, the first one is kind of easier because we only have 3 values here, x, px, and I can have 0, 1, and 2. So for px equals to 0, px p0, I have 9 on 16. P1 is the middle 2. We're adding that. It's 6 on 16. That's 3 on 8. And for the third one, for x equals to 2, I have 1 on 16 because there's 2 clubs. Okay. A is easy. Okay, we set up the tree diagram. We can work out what we want. Let's have a look at B. B is the thing I want to emphasize. Again, I still can have club, not club, club, not club. Okay, make a longer one. Club, not club. Okay, what's the probability for the first time? Club. 1 quarter. What's the probability for the not club? Okay, good. What's the probability for first club here when you select a club already? Good, everyone get that. 12 over 51. For not club. Okay, and after that? Yeah, you still have 13 club and you have 51 card, and this is 38 over 51. We have a not club taken already, have 38 left. Okay, so the probability of all of these, I don't want to calculate. Well, we have cats, so I'll open the cats first. But before that, well, this is a 1 on 17, I know that. This one is a 1 on 17 because the 4 and the 12 get cancelled with a 3. 3 and 51 get 17, so that's 1 on 17. And the other ones I can do by cats. 1 on 4 times 39 over 51. And that's 30 on 68. And if I get 3 on 4 and 13 on 51, same thing, 30 on 68. And the last one I will have 38 here. That's 19 on 34. Okay. For x values, I have 2, 1, 1, and 0. Okay, 2, 1, 1, and 0. So I can set up this. Okay, for 0 I have 19 over 34. For 1 I have 13 over 34, and I have 1 on 17. Okay, after simplify, it's quite easy numbers. Okay, there's no problem with this particular question here. Now, if I want to change the question to to what? To choose 3 cars without replacement. X equals to the number of clubs. Okay, you don't need to do it. Okay, don't need to do it. What difficulties you might have? Or say what difficulties you definitely have. Okay, we have club, club not, club, club not, club, club not, club, club not. You don't need to draw this, okay? Do not draw this. It's a waste of time. Okay, so you know the probability here is 1/4. Here is 3/4. Here is 12 over 51. 39 over 51, you know that is 13 over 51, and this is 38 over 51. Okay, what's the probability here? 2 has been chosen already. What's the probability here? Okay, here, 50. Here, 39 over 50. Do you want to keep going with it? How long you might need? That's only 3 selections. Only 3 selections. Okay. How about if I get 4 selections? Just no way to do it. Okay. It's just, you can't. Takes a day, and exam over. That's it. Okay. Tree diagram is not possible to find out. Well, it's possible, but it's almost impossible. It's not practical to use this method to do on exam. Now that's why I ask you don't write it, because I will just clear it. Okay, think about this. Do you remember this question from last year? I have a class of 25 students, 15 boys and 10 girls. I want to select a committee of 3. What's the probability of getting 2 girls? Do you think it's the same type of question as this one? I have a class of 52. I have 13 people, 13 male, and 39 female. I want to select a club, like team, committee with 3 people. I want the number. What's the probability of the number with no females and only all males? What's the probability of getting 1 female and 2 males? So what's the probability of getting 2 female and 1 male? And what's the probability of getting 3 females and 0 males? Right? It's the same type of question. I can change it. Okay, so for this type of question, what's the key thing is we don't replace things back. Without replacement. This type, they are equivalent because we don't replace. Okay, we don't replace. This is called the hypergeometric distribution. Okay, it's a useless distribution because it's not on the calculator, even though you know the name, it doesn't help. You need to do it by hand. What happened is, why I can't replace? Why I said this is the same type of question? Well, for the committee question, I haven't said you can't replace the people back, but will you really replace the people back? You won't. You select, okay, you select yes. Me and then put me back. Second selection, you still can have me. Possible. Okay, replace me back. And third selection, have me again. Okay, lucky, have me 3 times. I represent 3 people in that committee. It's not possible, okay? It's not possible. So some question is already without replacement. Okay, some questions already can't like replace things back. It's without replacement. So it is the same type of question. Now I have the question is, you know, like in this case, okay, I draw a really big one. Really big bottom. I have X. and PRX equals to X. It's 0 selection. I have 0 club, 1 club, 2 clubs, and 3 clubs. That's what we might have. Okay? Okay. Now, I want to think about this. What's the total number of combinations? You must know this, okay? Chapter 17 will come back. It's exactly the same type of question. You must know how to do this. Okay. 3 selections from 52 different cards. Okay. Every single card is different. They all look different. I want to select 3 without replacement from that. What's the total number of combinations I can have? It can't be 6, it will be more. Because, for example, the 3 ace. Any 3 ace, that's 1 combination. 2 ace, 2 twos, that can, 2 ace, 1 2 can be another combination. There will be a lot of combinations. What's the symbol to represent the combination? You see something. NCR. Remember that? Combination NCR. How many we have in total? We have 52 in total. How many do we want to get? Without order, I want to get 3 out. That's the total number of ways I can have 3 cards chosen from a deck of 52 cards. That's my denominator. Well, that's with no restriction at all. I just pick any 3 cards. Okay, any 3 cards. What's the total number of ways I can have it? What's my numerator should be? My numerator, okay, I have 13 club, 39 not club. If I want 0, X equals to 0, how many I should get from the club group? If X equals to 0, how many I want to get from this group? How many I want to get from this group then? A selection of what? 3. So 3 cards here. So what I should write on top is 13 I want to select 0, but 39 I want to select 3. So similarly in the next case, I want to have X equals to 1, which I want 1 club. So I want to get 1 from the 13 group, and I want to get 2 from the 39 group. And for the 2, I want to get 2 from the 13 group, and I want to get 1 from the 39 group. And the last one, I want to get 3 from the 13 group, and I want to get 0 from the 39 group. That's the numerator. Okay, that's the numerator. That's how many combinations satisfy what I want. Okay, satisfy what I required. And then divide by the total number of ways I can make the combination. That will give me a probability, and that probability is X equals to 0, 1, 2, and 3. Okay, NCR can be written as NR in this way, and that equals to N factorial over R factorial times N minus R factorial. Some special values we have is 0 factorial equals to 1. N select 0 equals to 1. N select 1 equals to N, and N select N equals to 1. So that's just some special quick evaluations we have here. So for example, in this case, 13 0, that's just a 1. That is a 1. 13 select 1, that's a 13. 39 select 1, that's a 39. Just some quick evaluation, like simple ones. And 0 factorial is a 0. It's not 0, sorry, it's a 1. 0 factorial is a 1. But instead of using the NCR formula, like the N factorial over R factorial over N minus R factorial, like it's quite large, okay? The number is quite large. Like 52 select 3, can imagine 52 times 51 times 50 times 49 until 1, it's quite large. So what we can do is by calculator. So how to do by calculator? For example, the first one, the denominator is 52 select 3. So manual 5 and 3 is the combination. Okay, probability and 3 is the combination. I want to have 52 card, comma 3, select 3. That's my denominator. So I can copy that and paste that here. Now the top, I need 13 select 0 times 39 select 3. Okay, so that's what I have typed on top. Okay, make it higher for you. Okay, I get the first probability is 703 over 1700. I'm not going to evaluate the rest. It's just something shows you how to do the probability. It's just this NCR method. NCR method is very important because we will still use it later. Any questions? Oh my God, it's about class about to finish. I feel it's just the start. Any questions we have? Okay, if you don't have any questions, just try to use the same method to do the second B, part B again, like using the same method, and compare the value should be the same as your tree diagram. Make sure you understand it because it will come back again in chapter 17 for this particular method. It's the new study design. Okay, it's new study design, get this come back. So you need to really know what to do with it. All right.